So let's go to the drawing board for a second here. Um, so okay, I don't think we lost anything there. Okay. Um, yep, looks good. Looks good. Yeah, I saw this. This looks interesting for the just auto ML stuff. Um, so I think it's very similar to what we're saying in here. Um, so, yep, this is what Alice is going to do. Good description. So, um, okay, so I think this really matches up with the last video, 28. Okay, so let's start a new one, and this will be for this video. All right. Okay, so 30. Um, hmm. Okay, so yeah, what I realized was we're making this too difficult for right now. Surprise, surprise. All right, so we're gonna draw some mermaid diagrams. Let's go pop open the live editor. Boom, boom. Okay, let's draw Alice and Bob. We should have started with this. Seems so obvious now. All right, so where's GitHub? So we're drawing out that architecture that we had here. We're going to drill into that. Let's grab this. Okay. Alice and Bob. Okay. So Alice has file. Alice uploads file to HTTP server. Um, she creates a DID doc containing the URL. She adds that to the chain. Bob grabs that from the chain. He inspects the public signing key. So he looks, and so this is where this flow is going to become. So this is subgraph. We're going to pull Alice, Bob, and the file out of here. Yeah, this stuff goes here. Okay. So this would be shared key for our, okay, yeah, shared key between DID and SSH key. right? That was the approach we started with, right? Because it's the fewest steps. Now, what did we find out? Well, we found out that, okay, yeah, here. We found out that we were told explicitly not to do this by the world's best crypto people. So we're not going to do that because that would probably be, I mean, that would be pretty, we really, that would be pretty blatantly a bad idea. So, so we're just going to leave it here, document it as an option that was considered, and we're going to copy paste, and we're going to say, what is the other flow? So the other flow is this ephemeral SSH key, ephemeral SSH key for DID signing. So what this means is that what we're going to do is we're going to upload a, we're not going to actually use, we're not going to keep this key. So the key that we use, so previously we were going to keep the key and we were going to use it for SSH, and then we were going to use it for, we were going to use it to SSH into things, and we were going to use it to auth to GitHub, and we were going to use it to um, also be our root identity on the on chain. So clearly, in hindsight, that sounds like it sounds like a bad idea in hindsight when you say it all out loud. So, and we were told not to do it, so we're not going to do that. We're going to instead, um, we're going to instead uh, create a short-lived key, and this is very similar to what the folks at Sigstore are doing with Sigstore and Cosign. So basically, we're going to create this little DID that's just it's a throwaway DID. Its purpose is only to establish a link in the chain. Um, and so let's see, how would we depict that? So yeah, so Alice and Bob, those are their root key. So this is Alice root, Bob root. Okay. All right. And why am I saying, oh crap. Why am I saying root? So because this is where we're going to root our assumption of identity in Bob. So as far as these DIDs are created, if we're saying there's one DID that equals Bob as an entity, that Bob chose to maybe map every single other DID back to if he wanted to, um, that will be, Bob's root DID. And so what we suggested in the first approach is that basically we share the key of Bob's root DID with, SSH auth and other things. And so, but basically the problem is the more you use that key, the more susceptible you are to attack, right? So what's your attack surface? Well, I mean, however many times you're going to load that private key, right, is sort of, that's those are the times when your attack surface is active, or maybe where you have to store it, right? So anytime you have to do something with this key, you've increased your attack surface. So, and if we were suggesting that we were also going to, so we were going to use it to auth to GitHub, and we were going to use it to do remote execution. So basically, if maybe left your if you left this thing on disk as a SSH private key, and you didn't set a password on it, then all of a sudden, now you have access to everything on your Web3 DID, right? So that is not a good way to go, and very obvious when you talk it all through. So because that would be very bad, right? So we're gonna properly segment things like we should have in the first place. Um, but this is why we do research. So, right, because you can't know everything, but you can do research. Okay, or let's say house, house root for everything. Yeah, it's like logging in as root everywhere. Bob root for everything. Okay, so ephemeral SSH key for DID signing as credential. Okay, so what are we suggesting here? So now what we're going to suggest is ephemeral key for DID, ephemeral SSH key for DID signing as credential. Okay, so what can we do? Um, Now it's when we get to have some fun. So we get to start playing with how these things really play out when you're messing around with these distributed identifiers. I think this made it clear. Um, uh, and we're going to draw it out because we should have done this in the first place. So we're going to establish some roots of trust, um, and we're going to map that out, and then we're going to show how we're using it to access different services. And so we should probably throw on our SSH server, and so we should put it maybe in front of our HTTP server, right? So maybe we SSH into a box and then put it on there, right? So um, Alice root for everything and Bob root for everything. So let's take these and let's make them you know, uh, distinct root, right? So we're going to have one key now that's the distinct root and only used for that root operation, right? So we only pull this key out. We only pull this key out when we're doing something important, right? We're not we're not sitting around and pulling this key out all the time, right? And actually we're going to add, just to developer tooling root, right? So here's how we can do some rotation, right? And we're going to have to, the one thing we haven't accounted for here is like revocation. I'm not sure how that's going to work, but we're going to need to find out a way to do revocation. So, oh, how are we going to do revocation? That's right. So revocation is basically going to be one of the things that gets wrapped up um, into the risk analysis portion of the smart contract with risk embedded risk analysis. Um, so okay, so if we'll put these contracts out there that will contain, DIDs that will link to models, which will be doing the risk analysis and deciding whether they want to, bid on further subcontracts or and bidding on further subcon or calling or doing call for proposals on for subcontracts could even just be amongst their own agents, right, and not out to subcontractors, but just to subcontract to themselves effectively. So and that's for job execution, right? Or any operation execution, which an operation could also be a flow. So um, when they're sitting out there doing that, right, and these agents are waiting and receiving jobs, right? They're sitting there and they're waiting these little operations, right, waiting for their input events that will trigger them. So um, let's see. So God damn it, now I got all over the place. Um, So when they do that, they're going to basically they're waiting for jobs, but they're waiting to see if they want to bid on a job, and so strategic plans are basically like putting out these jobs. They're putting out these jobs, these system contexts, right? They're saying, hey, I thought about this. Just, here's FYI. Add these to your data sets if you wish, right? And you can query them to say, hey, I need some of your memory, right? Can you send me some data sets that you logged that were about these properties, right? Can you go query your graph of your, past executed or theorized system context, right? And can you send me those because I have a problem I'm working on, and it requires that background knowledge. So what all is the information that so that I can start mapping that and this is from an agent perspective, right? Um, so so um, so one of those things is going to be this, these this the let's see. So the prioritizer, right? That's sort of what decides what contexts are executing at what priority within a given running orchestrator context. So that um, that let's see. So that basically can receive basically whenever an operation is executed, you can throw the prioritizer on the front end as a overlay. So you can basically apply an overlay across the board. You can sort of say, you would basically say there's a default overlay, and when um, you have the ability to set the default overlay via an environment variable or a config flag, but it must be set explicitly. You can't not set it explicitly. You should export it in Environ or whatever if you want to do it, but it has to be visible somewhere that's not on disk, right? That's not, or at least if it's CLI flag environment would be like a 12, a 12 factor app. So um, but basically, um, yeah. So let's see. Okay. Um, okay. So environment variables. Sure. Okay. 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 All right. Message that contains Alice distinct root. Okay. So yeah. All right. Okay. Let's refocus. I'm getting off. I'm explaining too much stuff. It's in the thread. It's in the thread. I don't need to explain it right now. I need to do the work right now, because I'm getting thrown in all sorts of directions here. All right, so developer tooling root, dev tools root, and then Alice GitHub proof. All right, so if you use Keybase, this is kind of going to be familiar. So we're going to basically post something up there, right? And what we're going to post, well, we're going to post a public key, but we could post whatever we wanted. We're just going to post a public key because it's easy, and we can check very easily by um, querying the GitHub ID of the person. So if they say, hey, I'm this GitHub ID and here's a public key that's in there, then all right, great. I can go ask GitHub, and I at least know that GitHub is somebody that trusts you. Now, this is where that prioritizer comes in. Is it says, where is this contract coming from that I'm bidding on that I might want to prioritize for scheduling? And it checks the provenance information, and the provenance information is just that linked chain of data, and it must present that up front within it has to present all those DIDs, and because when they put an offer out there, it has to say, here's all the things that I might want, so that they can show up ready and say, hey, here's all the things I can offer, and here's proof that I can offer them. These levels of assurances, any review systems and stuff gathered, all with roots of trust back to whoever said, hey, these are the things that I trust. You have to make sure that whatever your data is coming from proving that you can do this job is being signed by somebody in this group, right? Is org or these keys. Um, that and you're adding in the models because the models are what allow this to operate, like in a generic sense because they can just sort of, you're training them to the point where they know your general desires so they can be out there like doing things for you and um, acting in variable environments, but you could also, program it to be very specific logic gates if you wanted to, right? But that's where sort of the models fit in is that, okay, I'm this percent sure, right? So what is the risk of executing this thing? Um, and if you're like, meh, it's within my risk tolerance, for whatever the reward is, go for it, right? Just hit execute on it. And, then you basically, if you're doing like remote execution and you notice that you're, that something else says, one of your boxes got popped, then, um, you know, you shut it down, you turn it off, you reboot it, whatever, acceptable losses, you factor that into the risk is like the uptime loss on rebooting the VM, if you detect something malicious, right? So yeah, yeah. So and yeah, so you can basically make this like peer-to-peer distributed server backend where people can run each other's code. Because you can define your code as a data flow and then you can define what implementations you trust. And so you can trust the orchestrator and you can trust the implementations and then if they provide the attestation information, then you can trust that they are going to do it correctly, right? But if it's something, that's just like, hey, scrape the weather for me, right? I don't need an attestation. Like if I notice you didn't scrape the weather for me and it's not the updated forecast, it's not the end of the world. Um, so I don't really care if there's attestation information with the weather every day, right? And so you can put that into the contract that says, hey, I'd like somebody to go run a bot right on their server that's just sitting there that's got idle time. And that checks the weather for me, right? And so the person on the server says, okay, hey, I can run this series of operations, right, from these sources that we both trust. Um, and they agree, okay, yes, this is the specific implementation of those operations that you're going to be using. These are the specific assurances that you can provide me that you're running them to the specifications that I say, and this is the reward that I'm going to provide you for doing that, right? And then you can set these, basically fee schedules and you can set reprioritization trigger events and you can declare all of this up front, right? Because these are declared as like inputs and sort of side effects that could happen in these manifests, which are the DID methods. Okay, so Alice GitHub proof. Okay, so we're going to throw this key away. So basically, let's see. Alice distinct root, DevTools root, GitHub proof. Okay, we're going to do the same thing for Bob. We don't want to give him any less trustworthy setup here, old Bob. Okay, so where's our ephemeral setup? Okay, let's give old Bob his link here. Okay, there we go. So Bob inspects Bob distinct root. Bob distinct root. Okay. So what is this? Okay, so Bob distinct root. Verify message. Okay. So verify message. Okay, so this is verify Bob root for everything, and this is verify Bob GitHub proof. Okay. Bob root for everything. Where are you? Okay, now they went away. Okay. So, all right. What do we got? DID doc. Okay, so Bob root for everything. HTTP server. Okay, so Bob. So let's say maybe Bob root for everything. Okay, file, Alice root for everything, HTTP server. So we're trying to say basically Alice uploads file. Alice creates DID doc for file. So Alice creates a DID doc for the file using her root for everything. All right, this has to go in here. That's what's going on. All right, HTTP server. Where are you? Okay, you're out there. Great. Okay. All right. All right, where's the file? Okay, file. Why is the file in there? Should be in its own spot. All right, goddamn. Do I have to subgraph over here again? All right. Okay, so let's just say this is local disk. What was it? Alice? Yeah, Alice. Local disk. Okay. All right, there we go. Now there's the file. Okay, so Alice root for everything. And then this is developer root. And then ephemeral. Okay. Or let's see, this would be. Okay, file sharing root. All right, so maybe Alice has many sets of keys, and so she may even go as far down to file sharing root. Okay, so Alice file sharing root, Alice, Bob, chat, root. Okay, so, hmm. So what I realized is this is gonna look exactly like our operations. So we're gonna have, you know, one operation. If we want to develop a chain of trust, we would have one operation take, the key that it needs um, to sign it, right, and then produce the next thing. Um, and so we end up with this data flow which re-rolls all the keys. Um, so so yeah, so we'll end up with the data flow that re-rolls all the keys. And to do that, let's see. So if we end up with the data flow that re-rolls all the keys, the DIDs that get created. Okay. So what happens here? So we have this distinct root, developer tooling root, file sharing root, Bob chat root. So what if we wanted to write a data flow for this whole thing? And how do we know? How do we know? Okay, so we want to write a data flow. Yeah, so let's approach this from a different angle. We want to write a data flow. Ephemeral key, and let's leave the file out. Let's leave the file. So ephemeral SSH key used to signing credential. Yeah, let's leave the file out of this for now. Let's leave the file out. Yeah. Okay, so file. Okay. Yeah, this is just, yeah. Let's create the ID doc. So what we're going to show when we finally make this diagram look like it's supposed to, is we're going to show how, we can use all these. Um, we're going to create uh, input. We're going to create flows which basically derive the keys for us that we need to make whatever we want to happen happen. Um, and so these are like our auth flows. Um, okay, I'm struggling to explain this one. We're going to try writing it out. I may just play around here and not have commentary. So, and explore. So, Bob chat root. Okay. So, so we're trying to show. Yeah, okay, so let's just actually show the entire picture. Okay, so let's show Bob machines. Hmm. Bob share pool. Bob share pool. Okay, great. Okay. I think we can take our mermaid and make a data flow out of it. Okay. So then we'll fill this out. And we will put the DID message stuff in it. We will put the DID message stuff in it. So we're going to write the flow for this file sharing thing over HTTP. We are going to, so basically this says, this is, Alice says, send this file to, or we say, Alice, send this file to Bob. And what does Alice do? That's what we're going to draw here. And then we're going to make operations for it. And we're going to make it so that the current DID COM code that we have here with all this resolver pure DID stuff, we're going to bake that in to the input network. And then we're going to have the operations within the input network reach into the orchestrator context and talk to the input network directly. just in a because so this is something where we're using a specific right. So this is the implementation knows how to talk to the orchestrator in some way on this API level, right? And so there's this tight integration there. Um, yeah, it knows how to talk to the input network. API level. Yeah, so there's a tight integration there, and we need to manage that tight integration somehow because we want that type of API to be visible. Um, you know, we want that relationship to be clear because you don't want to. This is how you end up with one of those situations um, where like Python with the C Python interface when they need to change it, it's like it's a lot of problems, you know. Um, so okay. Um, so you need to declare if we can declare up front when something is going to maybe we can have a allow list. Maybe we can have an allow list so that just so that we're tracking things right off the bat, right? So let's not have anything because this is going to get out of hand, right? So um, vim dff df memory. All right. So where are we going to look at this? Oh yeah, I'm really excited about those NFTs as our distributed locking mechanism. Problem solved. Fantastic. That was a tough nut to crack. I had no idea how we were going to solve that one. This solves it right for us. Okay, so let's go look at the. God, this is terrible in here. These are going to be great data flows. Okay, so that's okay. So and memory net, input network context. Okay, so we want to look at operation implementation. Yeah, we want to look at memory operation implementation network, and we need to make sure that we go back. Here's a to-do item. We need to make sure that we go back and we uh, re double check. I mean, we're going to have to write schemas for all these. Um, and when we actually, you know, I think what we should do is we should, yeah, what the hell? I mean, we can just have, we can just have something because we can do the introspection. I bet Fast API has that Open API v3 stuff. I bet they can do the type inspection on this stuff. And if not, we'll just use inspect. We've got plenty of stuff that does that. Well, maybe we just, yeah, we already have a bunch of code that does that. So we'll just use that in the definition discovery code. I think there's some typing get origin stuff in there, which gets you the type information. So, so we'll use that. Thank you, Sudhanshu. That was good stuff. Um, all right, so on instantiate and instantiable. Okay, so here is a really good place for us to add validation of the allow list. Um, so what could we do to ensure that that happens? Okay, so we want to make sure that we don't end up with operations. Let's see. So we want to make sure that we don't end up in a situation where a operation or a memory. We want to make sure that we don't end up in a situation where an operation implementation network context doesn't check the allow list of what operations can be like what operations can take wait yeah what operations can take what inputs oh no yeah what inputs And the way that we would do that is we check if a system context is valid by um, checking the allow list. So um, and the allow list is on the operation level. Where's my notes? They're on my phone. Okay. Allow list required of which inputs come from which sources to be valid. Validate in terms of data structure spec. Um, Chains of trust just become valid to return true, or else none. Operations for validating provenance chain. Identity aware context means the prioritizer is checking the identity to see if the auth is still valid to schedule the next tick of the context on for that op for that context. Okay, Wardley maps for Web3 and Edge. All the major dependencies. Oh yeah, so we want to do when we're doing analysis of strategic plans, when the prioritizer is doing analysis of strategic plans, it should look across the network and judge the relative scarcity of commodities, and then or judge the relative scarcity of digital assets, and come to a determination of effectively come to the relative scarcity is a part of the equation, but effectively come to a determination about, what is the state? Is it something that we can assume is a commodity? Um, Sort of in terms of like investment in trains of thought, right? So you want to predict out there, you want to use that data that you're grabbing from the network, and you want to predict out there, and you want to say, you know, what is what are these things that I see becoming a commodity to where maybe we just think about this a little bit more and then we execute later, right? And basically, having a strategic plan that sits there and thinks about that type of thing, right? And is evaluating other system contexts that get presented and says, I'm not ready to bid on that one yet, right? I think, maybe later. And so then it would stop, the gatekeeper from executing it. All right. Yeah. And so then if we have the operations method, then we can check if they're valid. So for the allow list, all right. And we were just doing a little detour for that. So yeah. Okay. So how do we get to this thing that we wanted to show? Well, what do we want to show? Well, we want to show our next immediate goal is to show CVE bin tool running across um, multiple machines where we're sharing the mirror. Um, and we're going to spin up CVE bin tool as an operation, and we're going to use CVE bin tool as an operation to scan a directory. And when we do that, we're going to do it in a distributed fashion. So um, we're going to be issuing uh, effectively, let's see. Yeah, we're going to be issuing these contracts with TBDEX, and then we're going to, do the bid process, and the contracts that we issue are going to be these, system context, and the system context is just an invocation of CVE bin tool, given a particular input source, right? And that input source is going to be, provided by a data flow like or an operation, right? So it would be, provide input to CV event tool, right? So in CV event tool takes, a directory, for example, right? So we better feed a directory into CV event tool. And so whatever flow that we put in front of that to produce a directory, right? So be it. But we better give it a directory, right? And so then that directory, so let's see, so that directory, hmm, hmm, that directory, we said basically we could have different, look at the locality and then tar them up in different ways. I'm just thinking, what's our immediate next use case and how do we get as fast as possible to that? Because I'm worried that we're down a bit of a rat hole. And okay, so, or a rabbit hole as it were. Okay, so where is our to-dos for down the rabbit hole? Okay, so we need to, oh yeah, so why are we doing this? Because we really need to establish this, you know, chain of system context. Um, so let's see. And why do we want to do that? Because we want to have an unbroken data stream so that we can train on this whole data set as fast as possible. Okay, so what are we going to do? We're going to encode to DIDs. How are we going to do it? We're going to, um, how are we going to do it? Okay, so we did this here, which is, we were doing this DID com stuff. Right, okay, so if we can do this DID com message where we send a manifest, right? Okay, so where's the TB dex? TB dex. And we were thinking we could basically make the currency a DID to a particular message or something. Okay. Message ID, thread ID, sender's DID, recipient's DID, specific message type. Any of the message values documented under the message type section are valid. The actual message content, created time, expires time, fully acquired URI. Okay. Okay. Source currency. Okay. Ask. Okay, so why is there only one currency? Okay, so we're just going to put source currency data type string source amount. Okay, so we'll say this is manifest. So we'll say, hey, I have, you can put up, you basically, you put out these, every time a system context is put into the network, because the input network generates a DID for each input, then there's going to be a system context with a DID on it, right? And we can have different flows that hook onto the front of that that say, hey, if it's a system context with the basically link it via the lineage for this execution. So each execution is a system context, and when it gets picked up and executed, you create a new system context, you link to the old one, and at the point when you link to the old one, basically, so do they have a diagram? Okay, perfect. Let's build on this diagram. Okay. Okay. So there's the diagram upstream. Okay, wait a minute. Come back. Okay, here it is. Okay, so ask. Okay, so let's just do this, actually. Let's go back to that mermaid and let's work off this. So this is more grounded to reality. Okay, so settlement request, settlement details, settlement receipt, offer accept, conditional offer. Okay, so ask PFI. Okay, and what are they asking us to do here? Oops. Okay, come on. Wow, all right. GitHub's glitching out. Okay. All right, where is the protocol again? Too many tabs. Where is it? Uh, TV decks. Oh, did I close it? Oh, that explains it. Okay, protocol. This is type body. Okay, body, and that's what's there. So, okay, so these things, the message ID, and I take it this is a DID. Let's see. Yeah, I mean, I take it this is a DID. Right, thread ID is set by the first message in the thread. Sender's DID, recipient's DID. Field data type question mark required. What does that mean? ID. Thread ID. Let's look for thread ID. String. ID and thread ID look like strings. Okay, thread ID. MIDI. Okay. Set up database. MySQL. All right. Example message. All right. So you run MySQL. You create this messages table. Okay. So let's see if we can be interoperable with this thing. Body thread token. Wallet address, bank name. What is this? From Alice to Okay. 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 Test. Okay. So ID, MID, thread ID, type settlement details from else. Okay, so ID and thread ID. So thread ID could be the previous system context, maybe. Or thread ID would be the input object. No, thread ID would be, let's see. Yeah, thread ID would be the DID, I think, that we're bidding on. Thread token. Thread ID, I believe, is the thread token. Body, type, body. Type settlement details. Receipts. Okay. Hmm. Okay. Target currency, USDC. Okay, so source currency blank, target source amount blank, target currency blank. Okay, so what do we want to do? We don't care about money. So we we don't care about money. So we care about source currency as a DID for the thing that we want to buy, and then source amount blank, and then target currency a DID that we want to produce. And a DID that we want to produce is basically like, let's see, source currency, target currency. Basically, oh, this is what I have to offer. This is what I have to offer. This is what I have to offer. What do you want to buy? I think I need to write on my whiteboard. This is what I have to offer. What do you want to buy? Okay, I think we're getting somewhere here. So source currency, target currency. Let's do an execution in Mermaid. And let's focus on source currency and target currency. So source currency, target currency. Okay, so what goes into source currency and what goes into target currency? And what is this? This is a ask. Subgraph ask. And okay, so context A, context B, or so context Alice, uh, strategic plan, suggest, okay, suggest run data flow, basically. So we're suggesting a run data flow, and we put it out there on a network, right? So strategic plan suggests run data. So this is the same as submitting a system context for execution, right? So this is start a context, right? Or let's see, suggest start context, or suggest execute context, right? And so strategic plan suggest execute context. Okay, so we suggest that we execute a context, and so then the context goes into the input network, right? And the input network creates a DID. So input network. So basically, this is uh, uh, run data flow is triggered via context provided as via system context provided as input. Run data flow is triggered via system context provided as input. Okay, so the input network, this sits here and it receives the that input, right? That that input set context. Um, it's like an input set context plus a data flow. Um, okay. So it goes to the input network. Input network creates a DID doc. So context. So parent context. Uh, you know, uh, uh, attests relationship to via method to peer DID. Okay, wait a minute. Or can we just use DID com? Right, so anonymous encryption. Or let's see, authentication example. Most common case. Build unencrypted but signed DID com message. Authentication encryption. Anonymous encryption. Okay. So this is, this is basically we're sharing. We're in the sharing mode. So our implementation or our input network has been instantiated with parameters that says it's going to, not sign for when messages are going to these parties, and it's going to, you know, uh, have operations which are sending inputs to chains over different transport protocols, right? So, um, okay, so okay, ID. So we're going to send this out there, but we want to do a broadcast, right? So anonymous encryption example. So we want to say for given recipient, we want to do it for everyone. Lacks confidentiality and integrity guarantees, but is reputable. What does that mean? Is not packaged into any protective envelope. Built and unencrypted but signed. Okay, the origin plain text. The sender can't be proven to the recipient by authenticated encryption because this recipient is not known in advance. Adding a signature when one is not needed can create rather than enhance security because it relinquishes the sender's ability to speak off the record. Okay. So, signed from Alice. Message signed as Alice. Okay. So we're going to have, yeah, pack sign. Okay. So we do the pack signed, and we say signed from Alice. Okay. So we're going to have we say signed from Alice, and then, but we have to say to Bob. Why do we have to say to Bob? Can't we just say to everyone? I don't understand why we have to say to Bob. Can't we just sign some data? Or maybe that's just, maybe all we would do then is, do we even need, let's see. Do we even need the purity ID stuff? Okay. So if we just do TBDEX, if we look at TBDEX, right, and we said source currency is a DID and target currency is another DID. Source currency is a DID, target currency is another DID. So I want to trade you this for this, right? So this is my offer. Okay, so that is everything with provenance information that I'm going to be able to offer you. Okay, so basically ask from PFI to Alice, ask from PFI to Alice. Okay, so the PFI says, Alice, would you like to turn source, would you like to turn 100 USD into USDC? Okay, so Alice, would you like to turn blank into blank? Okay, so but we can basically say, so these don't have to be DIDs themselves, these are just messages. So if you wanted to pass these messages via DIDs, you could, but you don't have to. Okay. Okay, so the thread ID, okay, so the message is a JSON web message. Essentially, we don't care about offer, conditional offer, ask, conditional offer, offer accept. ATV submission, settlement request, settlement details, settlement receipt. So we offer accept IDV request. What is IDV request then? So is there that white paper? What does the white paper say? Hmm. And price exchanges to account for perceived risk and specific requirements. Hey, that's what we're talking about. Oh, this is perfect. Okay, building on top of DID system lays out a trust model in which trust is governed through dispute verifies your trust. It's ultimately in the control of individuals, implementers of Encryption. Protocol itself does not rely on a federation to control permission or access to the network. There's no governance token. It is in its most abstract form, it is an extensible messaging protocol with the ability to form distributed trust relationships as a core design facet. The protocol itself has no opinion on what the optimal trust relationship between an individual wallet and a participating financial institution should look like. The nature of the trust relationship will never be universal. Different jurisdictions are subject to different laws. Okay. DIDs. Okay. DIDs are linked to DID documents, a metadata file that contains two primary data elements. Cryptographic material that DID owner can use to prove control over an associated DID, routing endpoints for locations to be able to contact, identity hub, personal data storage, and relay net. DID methods may be implemented for very different ways. The system must be open, public, and permissionless. The system must be robust, censorship, tamper evasion, employment. It's record probabilistically finalized and independently deterministically verified. Okay, so yeah, so this is basically, this is saying these are the exemplar methods. Okay, so if you implement a method, this is the things you should strive for, right? So we're saying that every operation could be a method, right? So, um, and then, we're going to try to add in some extra stuff on top, like, collecting the provenance information for us to enable some of these things, right? We can't do everything for the implementation, but we can try to do some sitting on top. Probabilistically, yeah. Verifiable credentials. Credentials are part of our daily lives. Okay. Verify. Zero knowledge proof. Data and storage. Data hubs feature semantically encoded message data and data inferences that provide inference. APIs a party can interact with simply by knowing the semantic type of data they wish to exchange. The diverse set of interactions and flows can be modeled within interfaces by externally codifying sets of message schemas and processing directives to form meta protocols. Yeah, okay, so these are manifests. So, like, this is the inventory, I think. Issuers of verifiable credentials. All could issue an evaluation of PFI. Had a negative experience with the circulate and amongst this network, effectively acting as a verifiable reputational feedback. Perfect. Sent it may appeal to an issue of potential change. Great. Wallets access agents for individuals or institutions by facilitating exchanges of PFIs. More strictly, well, provides secure encrypted storage for verifiable credentials. PFI discovery, client identity hubs, receiving, offering, and presenting VCs. Client digital signatures, storing transaction history. Okay, so that's what a wallet does. So a wallet is basically where we'll store everything, all the, okay, wallets deployed here. TBX protocol significantly simplify the user experience for their customers seeking to move assets between whatever in crypto. Individuals or organizations would no longer be required to first onboard through a separate centralized exchange to produce crypto assets with payment instruments before transferring those crypto assets back into the wallets. Individuals or organizations could leverage the Okay, so basically this allows you to say, hey, I trust that you change the money elsewhere, right? Protocol enables wallets to provide a streamlined customer experience with direct on and off ramps between the traditional and decentralized financial worlds. This means customers can use shelf custody wallets without having to give up convenience to exchange for security or self-hosted options. Okay, participating in financial execution, they offer liquidity. So, PFI, identified via DIDs and VCs. PFIs can be regional banks. Okay, so these are things that have basically they have access to payment systems and the ability to see payments in exchange for tokenized cryptocurrency assets or vice versa. Okay, so we are going to operate both the participating financial institution and the participants. And Alice, obviously. So Alice is going to be her own PFI as well. And so you could look at maybe Bob. So Bob and Alice are both going to have their own PFI, and that's how they're going to say, hey, I can, I can, let's see, I can change, this unexecuted manifest into this executed manifest is what we're going to say, right? So ask to change unexecuted manifest into executed manifest, bid change executed manifest or change unexecuted manifest. Or that's okay. All right, I have to pee. I'll be back. And I think we're gonna use